This is part 2 in our low voltage diagnosis video. One thing you're going to notice is that it's cutting back and forth between a system that I'm working on, a heat pump, and then a straight cool unit that Bert is working on with some apprentices. And these are actually happening simultaneously, but we're kind of cutting between them so that you can get a sense of a couple of the problems that we're diagnosing. In order to make it more enjoyable, just to kind of attempt to follow along with us diagnose as we're diagnosing. There's kind of some strange things that show up along the way, but that's how it goes in the field, right? Things happen, and I don't want to edit out the good with the bad. Also, before we even get into it, I know some of you are going to comment about the blood spot on Aaron's back. It wasn't a big deal. It looks like he jabbed himself with a nail while in an attic. Nothing major, but you know, hey, sometimes you bleed a little in our trade. The people taking the video really wanted me to make him change his shirt, but I thought, you know, hey, look, we're doing a class. This is real life. This is what's happening. You get to see the unvarnished look at what it looks like teaching at our offices at Kalos. And we're going to go through a series of a couple things. So we're going to be splitting up and starting on a couple different units, but I want to start with a couple more simple things. Eric has one, and then I have one. So I want to start with one of the most common problems that I see techs do, and that result in shorts and all kinds of problems, opens, whatever. They'll take a wire, regardless of whether it's 8-wire, 2-wire, 4-wire, 5-wire, whatever it is, and they'll do some version of this. What's the problem with that?
You just potentially nicked it down below.
I just potentially nicked it. And I don't know if I actually did or not, but most people, when they do that, they're going to nick right there. So what's the right way of doing it? Come here, Aaron, I want you to come demonstrate. Come demonstrate for all of us with your Crocs and socks. You are wearing Crocs and socks right now.
All day.
I appreciate that, yeah.
Looks like you're just wearing socks to me. Crocs.
We can't see them.
Okay.
They're chemical.
So he still stripped around it, but now he's going to grab one conductor, and he's gonna. All right, he's struggling here a little bit. All right, that's fair enough. Fair enough. We're done here. We're done here. I want somebody else to give a demonstration. Bert, come on, or yeah, Bert. Yeah, we'll have Bert do it.
I'm going to cut down the outer casing to create a line. It'll make it easier for me to tear down this line.
So he's making a split in the casing that now, when we grab either the string or one of the conductors, it will follow that split, and it'll come apart a lot easier.
Yep. And I don't see a string available here, so I'm going to use a conductor color that I'm probably not going to be using. And take it.
So on a heat pump, for example, if you're using 8-wire, what are the conductor colors you generally don't use? Brown, black are the most common. Yeah.
Yeah. I'm going to take it and tear it down the side. So I'm actually tearing the casing, and then I'm going to peel the casing back like this. So now I have a point. Pull this down a little bit just to show people that I did a good job when they come later.
Mm-hmm.
You actually know how I did this.
Yeah.
And then I'm going to cut off the point that I first cut into to make sure I cut any nicks out. So then I'm ready to go.
That's exactly how you want it to look. So then you can cut your extra off, and it's actually rolled back. So now it's
better not to cut your extra
nice there. Don't cut your extra.
Yeah, it makes you roll that into the metal edge, so the metal edge doesn't cut in to the wire when you're sticking it into the unit. Grommet. They could call it a grommet.
Okay.
It's like a homemade grommet. You just roll it up and stuff it in.
Okay. Got it. I don't really know what you're talking about, but that's fine. So the point is that I don't on a thermostat wire. I don't want to see you doing any ring around the rosy, because even if you cut off the part, you ring around the rosy later, it's still not an ideal way to strip through. When you cut into it this way, now it gives you a path that you can then peel away. Do you agree with that, Eric?
That's what I was
Yeah, okay. Well, I mean, if you have a string, and but again, I don't like your way. My way's better. Do it my way. It's simple. It's really simple.
It's almost impossible to grab on that string.
Right, even though you've been doing it the other way this entire time, you're absolutely going to do it my way now. Yeah, I'm sure. I'm sure. I'm certain of it. Okay, so what's that?
No.
Wire nut off all the unused ones? No, not generally. I mean, generally in residential, we're just wrapping it back around the base of it, generally. But the most common causes of problems, especially in newer installations, are what we just talked about: ringing it, nicking it, pulling it through, and nicking it or scraping it when you pull it through the equipment. In residential new construction, especially when metal studs are being used,
one of the most common causes are pulling it through a metal stud and chafing it when it goes through the metal stud. So anytime you're running a conductor of any type through anything, you need to make sure that there aren't any sharp edges at all. And the best way is to just always use grommets. Use a designed grommet or connector rather than just pulling things through metal openings. Just a important practice. Also, think about where we're going to route this. So let's talk about a heat pump for a second. So in a heat pump, if I'm routing some wires into an air handler, if I'm routing some wires, we got to pretend this is a heat pump here. I'm routing some wires into a heat pump through where the evaporator is. I think to myself, well, it doesn't matter if this touches the evaporator, right? Because the evaporator's cold. But the problem is that in heat mode, that evaporator coil can get pretty warm. Now, a lot of people will argue and say, yeah, but it's not going to get hot enough that it will melt the conductor. Yeah, but what happens if there's a system failure like a failed blower motor? Something like that. It can potentially get very hot. So that's just an example. Think about where you're going to route your cables and make sure that they're not going to be touching anything that's going to either melt the jacket or just vibration over time is going to damage the conductor. So those are all important things to consider. Next thing I want to do here is I want us to go ahead and wring out our wires. I want everybody to actually come up here now. Actually, I'm going to let Ryan do this. So go ahead and get both ends stripped back on this conductor, and let's grab a meter.
Don't use the string.
All right, so we're going to have Josh. Here you go, Josh. You're going to grab the meter. Well, but before you use the meter at all, what's one of the first things you do that we just talked about? Put it on ohm scale. Wring out the, yeah, that's right. So now it's not going to, okay, because you're on the mega ohm scale. There you go, that's fine. There you are. All right, so we know that our meter's working. Now, go ahead and strip off the end here. But I want you to go ahead and, you don't have to actually measure it, but if I measure right now between any two of these conductors, what am I going to measure with an ohm meter?
I'm not exactly sure, but I know you're going to measure something.
You're going to measure open or infinite. So there's a measurement, but the measurement is no path, open, right? Infinite ohms. Because why? On the other end, those conductors aren't connected to anything, right? Now, if I want to confirm that there is no break in these wires between here and there, how would I do that?
You can, what is it, test it to ground?
If you were checking for a short,
Gotcha.
that's something you might do. But this is the key thing. If there's a break in one of these wires, what is that called? It's called an open, right? So I'm checking for an open. And if I'm checking for an open, I'm looking for a break. I'm looking to find where there is no path where I would expect there to be a path, right? And so this is a common test. Now, this isn't always the way you would do this, but I want you to know how to do this. I want you to know how this works, because this is an area where a lot of new techs get confused, because somebody will say, especially a lot of senior techs who like the method of ohming out wires. That's actually not my favorite place to go to, but some people like that. And they'll say, did you ohm out the wires? And they'll say, yes, I did. But there's a lot of different ways you can ohm out wires, right? So this way that I'm about to show you is a way that you ohm out wires to confirm whether or not you have an open. So what I want you to do is strip back those wires a little bit longer. Or actually, do we have a wire nut sitting around here somewhere? So we're going to connect all of those wires together, all those conductors together, and then we're going to measure. Yeah, just connect them all together. So you don't put the two probes at the same place at the same time. You put this one over here. There you go. So now what do we know? Because now connecting from one conductor to the other is the same as connecting both meter leads together. Which means what?
Close. We have a
It
closed
means we have a
path.
closed path, right? It
no
means
break.
that connecting our two meter leads together, go ahead and connect them together again. What are we measuring? 0, right? And connecting these two to these two wires, what are we measuring?
0.4.
0.4, so we're measuring a little bit higher resistance, but they're essentially the same. So that means that these wires are completely intact, and we can measure all of them together. So we could measure blue and white together. Because they're connected on the other end, we would expect to see that, right? But now what happens if, let's go ahead and go here and mess it up. It's hard to watch, isn't it?
Oh my.
That's a fairly realistic break that you could get. You know, yeah, a mouse chews it, something like that. Now I want you to measure between these and see if we have an open anywhere. All right, so that means that, okay, but hold on, what did we learn? We don't have a path between green and white, but what does that tell us? Eli, what does it tell us? Where?
On one of those wires.
On green or white, right? So now we want to figure out which one it is if we can. Is it green or is it white?
Gotcha.
So what do we do? So let's go from green to a different color. Ah, all right, so which one is it? It's white. All right, so go from white to every other color and see if you get anything. Nope. Yeah, so we know now that we have an open white. An open white. Do we do this test if we have a, I don't know, blowing fuse? Is this a test you do if you have a blowing fuse? No. Is this a test you do if you have a blowing fuse? Is this a
No.
test you do if you have a blowing fuse?
don't think so.
It is not a test you do if you have a blowing fuse. I want you to really get this in your head. This is a test you do if you have a circuit that's not energizing. When it's energizing here, but at the other end, I'm not getting anything. So now you can check to see, all right, where is my open? But you can also just use voltage to do that. Go ahead, Eric.
What if I told you I would check that if I had a blowing fuse? Because I would want to check if my common wire is shorted to any of my other hot wires.
If you're
Without
common-
wire nut in the end, I would.
You're
wanna
not
be
checking. You're not checking for an open.
Yeah, we're saying that the time that you would primarily do this test is going to be, so you're okay, so explain to me again, did anybody else understand
If
what
I
he said?
have
Go
a
ahead, say it.
fuse,
Sure. Yeah. But if common was rubbing out
Okay,
on one of those wires,
okay,
it would cause a blown fuse.
right.
Well, he could test that by jumping all the wires together, but leaving common out of the wire nut. And then doing the test in here to see if any of those wires had a path to common.
Okay, yeah, sure. But not specifically this test that I just showed, but a version of this test.
yeah,
a
probably
different
wouldn't
version.
need to wire nut everything together because if you had the path, you'd have it pretty much all the time.
Right.
But you could.
Yeah, that probably wouldn't be the way I would do it, but yes, that is a possible method. But again, the key thing here is understanding what we're trying to test for, what we're looking for, not confusing opens and shorts. Opens, you're mostly going to have something not happening. It should be happening. Shorts, you're mostly going to have a blown fuse, or you're going to have circuits energizing when it's not their time to energize. But all this starts by first understanding the system enough to know what's going on here. Because that's what we're going to get into here in a second, is doing some diagnosis on what's going on and then working into the actual diagnosis. I want Eric to come on up here. Eric, come on up. And I want you, so you're going to have to hold your mic. I want you to demonstrate why you set this up and what it signifies.
This is a
We're gonna get
situation-
Tanner, you come up here.
That we ran into earlier, where we had the wire inside at the air handler. We could identify the colors, but the one outside was so baked in the sun we couldn't identify. We had 2 whites and 2 yellows. I want you to touch one of those wires to ground it, not all of them.
Okay.
I want you to figure out which one he's touching. So that one, what color is it?
Color is red.
So we would mark that one red.
Right.
So now that one's identified.
So what he's saying you would do in real life is if you can't identify on the outside, you could just take these and connect them to ground. If you have a good ground, but we just confirmed that we did. That test alone confirmed. If you checked all of them and none of them rung out, well, then it's very likely you don't have a good ground path. But we used ground. All I did was just took this red wire and touched it to the metal frame, and then she checked each one to the copper, which is also grounded, and could figure out, okay, now this is red. So I'm gonna do the next one here.
Okay, what do you got?
Green.
Red and green, so we would mark that one. We could just keep
We
on
can just keep
moving.
going, but we get the
No matter
point,
how
right?
many conductors, if none of them were labeled, if they were all the same color wire, even if he had the same color wire on his end, he could designate a color and you could designate a color outside. If you had 8 black wires,
Yep.
he could mark the one red and she figure out which one's which and on and on.
Yep, exactly. So do you all understand how we're using the ohm meter here? And I like to start with the ohm meter because it's the easiest one to just intuitively understand. It's looking, you're looking for a path. You're checking what we call continuity. Continuity is just a path, no path test. We're not looking for a specific ohm value or anything like that. We're just looking for, do we have a path or don't we have a path? But in this case, we're using it to identify, do we have an open circuit or to identify what circuit is which. Again, that's not going to be super common, but you get why knowing how the meter works leads to these sorts of solutions. All right, so now we're going to split up. We've got 2 different systems here, and I want to set the rules like I always do. I don't want us to guess. Guessing is the enemy of low voltage diagnosis. Here is the impulse. The impulse is to get close to where you think you have the diagnosis and then call a senior tech. That's a really bad habit. Call the senior tech once you've already done everything and you're already sure you're sure, then call to double check if you just want to, make sure you're not making a mistake. But don't call with half-baked information and some guesses thrown in. So that's the same thing we're going to do here. So each one of these systems already has a problem built into it. You're going to energize the equipment, and you're going to find the problems, and then we'll do as many of these as we can. All right, so you are not allowed to open the boxes. In this case, on this gas furnace, it's the box behind the thermostat. On this one here, it's back behind, because that's where I will create problems, opens, shorts, those sorts of things. So our main team here, the people touching tools, I want to be Aaron and Tanner, okay? Aaron loves low voltage shorts. He's really good at finding them. And I'm not telling you it's a low voltage short either. I'm not telling you it's a low voltage short either. A couple other things. We've got some magnetic jumpers here if you want to use them. And we have a couple of the Short Pro tools. So you can use these in place of your fuse so that way you don't keep blowing fuses. So I'm just telling you there's a problem. I'm not telling you what it is. Aaron, let's go. We got a meter here. We got a driver here. Let's start with, again, knowledge of the equipment. What do we know so far?
We know it's a heat pump.
Okay.
We know that it's indoors.
Okay.
Both of them. Blower is going.
All right, so what do we know? We know our blower runs.
Blower's running.
Okay.
Compressor fan is running.
Okay.
I know our refrigerant is flowing through.
Okay.
Thermostat is on.
Okay.
Float is dry.
Okay. So everything's
It is
working
in cool.
okay?
Yep, it is in cool.
What's wrong with this thing?
I'm trying to figure out what's wrong. Thermostat's set real low.
Okay, so what can we see on the thermostat?
Nothing.
Blank.
Nothing. Thermostat's blank. Okay. So where to next?
Float switch.
That's a guess.
No,
But yep, it's a good one. It's a good one.
I would
receiving
put
receiving any.
Okay, is the system receiving any voltage?
Check the
Okay, check the breaker. Let's start at the basics. Do we have power on at its source? All right, so check the breaker. Somebody? Anybody? So we got the breakers on.
we
All right.
still won't have power
Okay, so let's go look next.
because we've got the door off.
Okay.
And it's not.
All right, we've identified that. So we have a switch on the door. We already know from experience that keeps power off to our circuit board and power off to our transformer, right? All right, so let's close that switch. So let's go ahead and tape this shut.
So I had set this to a straight cool.
It should be 5. It shouldn't be cooling.
I know.
Why is it? It should have been in heat mode.
Right, I know.
So thermostat wasn't.
So why isn't it in heat mode? So,
Why isn't it in heat mode?
correct. So that's interesting. Now we're finding a different problem than we originally even thought we were finding.
Okay.
So that was the problem I put into it.
It was supposed to be
Right.
programmed incorrectly.
Right. And I was going to test you to see if you could catch that because you've never made that mistake before.
Actually, I used to make it all the time.
I know.
So it is in cool mode. We want it to be in heat. We don't want it to be.
We don't want it to be in heat, but it wasn't in heat. It wasn't in heat when it should have been in heat.
Yeah.
If the problem was not what we originally thought, which was that it should have been running in heat based on how I had it set up, now let's go ahead and run it in heat and see if it does run in heat. So what are you doing? You're just touching to see if
Just to make sure the reversing valve switched over correctly.
So you're going to feel heat here, you're going to feel cold.
So it is running in heat now too.
Yep. So for some reason it was energizing the reversing valve even when we had it set up for a straight cool unit,
Yeah.
which is kind of interesting.
And the reversing valve is coming off, so it is properly running in heat.
Yeah,
So
it
it's not
is.
that short of a
Yep. Okay. So anyway, we're not going to focus too much on that because
That's kind of weird. Though.
yeah, I'm not really sure why that happened, but
Still programmed for.
that wasn't my expected behavior.
Now, what's the danger of doing this?
Well,
What's the danger that I'm doing right now?
It's going to run, and so you're going to pull in.
But I'm doing this with power, and there's power on the backside of the switch, right?
Oh, yeah.
Yeah.
Shocking.
Mm-hmm. So, yeah, you can turn off power before you do it, or actually know exactly where to touch and not to touch. Our switch is now closed. What do we have?
Nothing.
Still a blank thermostat. We're gonna have to start moving into diagnostic now. We just tested our meter on live camera, so I think our meter's working. But where you want to check?
I'm gonna check if we're getting any voltage to the board because I don't see any light coming up.
Okay. So voltage coming into the board?
Yeah, so I'll open
High voltage?
high voltage.
You could check it there, but it does plug into the board.
Okay.
It's probably more accessible there to see if you have high voltage. But what voltage powers our board?
The 24 transformer.
Yeah. So we could go straight to the transformer and see if we're powering it. Where's the transformer plugging into the board here?
Right behind it. Right behind it.
Yep.
So it's coming through here.
So this is our power supply to it. This is the high side. And then the 24 volts comes out the other side.
And the reversing valve.
Right here on red and blue.
So it is properly.
Okay, so that's where you could check if you have voltage coming out of the transformer. So we're switching our meter to what?
VAC.
VAC.
Oh.
All right, so now I'm going to go ahead and.
So which one should I check?
Okay, so what if you're checking for 24 volts between what?
From red to
What's coming out of our transformer here?
the red and the blue.
Yep. So one side is going to be our hot, and the other side is going to be our common.
All right, so what do we got going on?
Alright, so we don't have blower's not going, system's not in delay. Does have batteries in it.
All right, you're always checking. He's checking the float, which is a good practice to
Put
start
the
with.
batteries out and system shut off, which means red.
Okay.
We're not getting. We're not
So, all right, so let's just talk about what you just did. So I'm interested in that. So you heard it go on and click off, but then you remove the batteries. Why did you do that?
I did that because a lot of times the float switches will trip, and if the batteries are still in this, you'll still have a display.
All right, so you're basically using that in place of a meter. I mean, you could have pulled the face off and checked with a meter, but instead you just use that, and I'm all for that. That's a perfectly good way to do that. So what you know is that you have no what?
We have no 24 volt.
No 24 volt power, right? We're not feeding the thermostat. Now, does that mean that the problem is in the R circuit? Because R's are 24 volt power.
Could be common.
Could be common too, right? Now, do we suspect that?
Yeah, but we're not sure yet. I'm not sure yet.
But what did it do when you first turned it on? What happened?
It kicked on real
It clicked
quick
and then it shut off. So, what's most likely? Because it did kick in.
We popped the fuse.
It's most likely that you popped a fuse, right? Because if it was, for example, a common that was completely disconnected, it wouldn't have come on and then gone back off again. So using your senses, I like what you did with the batteries, using your senses to diagnose is always first. So let's go ahead and get it open.
So we need to check between that. That's what creates our 24 volt circuit. You can see
So should I take that off or?
it'd probably be easier to reach if you take this off. Yep, there's a couple different ways you can do this, but let's just give you a little room. So put your meter in on the side of the spade on blue, touch the metal behind there, on here, and then your meter on red on the other side. And what do you got?
Nada.
Okay, so we got no voltage coming into our coming out of our transformer. Okay.
We check if we have any
Going in.
Yep. So we need to check if we got any going in. Okay. So this would be one leg here and one leg on any of these neutrals. All the neutrals are tied together. So find that spot where you can touch metal.
This one in neutral.
Any neutral, yep. No voltage. So we're still chasing our problem back further and further to power supply.
So we're not getting nothing from here.
Mm-hmm. And so where does power supply come into the board from the switch?
From the switch from the
So power will come in from our breaker. And like you said, first go into this junction box. And from the junction box, it'll be broken by the switch. And then straight to the board.
But what did it do
Are
when you
both
first turned it on? What
are we plugged in? Are both the leads
clicked and then it
plugged
shut
in
off.
on the
So,
switch?
I can't tell from here if they are. They look like they are. So let's just look at the diagram real quick. And it'll show us on the board which one of these is power coming in from the switch. So we're looking for line 1 is right here. So L1 is going to be our power coming in. And you see how it goes through the switch right here. It comes in and then connects to L1. So we'll check on L1 going into the board. So what we're checking is the power coming into the board and just not coming out to the transformer? Or maybe it's not coming into the board at all. So we'll go straight to the power source. We'll find L1 on here and check that. Yeah.
Is that the bottom one?
Yeah, it is. You have to come in from the bottom.
To
any neutral, yeah. Nope. Okay, so what have we learned so far then?
We're not getting power to the board.
Yep, we're not getting power to the board, and we're not getting power to the transformer. So we don't have power to our 24-volt generator, the transformer. And so now we got to keep chasing power back. Where are we going to go next? Where do you want to go next? What could happen in here that could break power? What human error?
Not wired it right. No.
Yeah, not wiring it right. But if it happens suddenly, what's another thing you could do wrong that later on would cause a problem?
Screwed in there, right?
Yeah.
Some kind of a
wire nut?
right.
There's a loose connection. Yeah. Loose connection. So it could be a wire nut loose connection in there.
Okay.
Or same thing on the breaker. So
Check out the breaker.
Before you're sticking your hands in there, you would want to check and just make sure that it's off, and you'd want to check each leg to ground. On this one here, that's going to be kind of tricky to do. You would actually either check it at the primary of the transformer, or you could just kind of put a lead into your wire nuts. So go ahead and do that quickly. So we are now on what? So before you even do that, we're going to put it on ohm scale. You already did it.
I did.
Okay, good. All right. All right. So you go each one to ground. That's a safety check because
sometimes you get one.
because you could have just one leg that's energized. Yep. And that actually commonly will happen. You have a disconnect or a breaker that has one leg that's still connected.
You pull a disconnect and one of the metal pieces gets stuck in there.
Yep.
Get a good
It's
little
It's a
shot.
fun day when that happens. I got 0. I tested both.
Okay, so we're good. All right. So now what are we looking for?
Now we're looking to just confirm that our fuse did pop.
Did it?
Yep.
Okay, so it blew. Now my suggestion is going to be to go ahead and pull that out and put in
I was gonna put in
our short pro.
our
Yeah.
short pro.
Which in this configuration is actually kind of tricky to do because you have
Alligator clamps with a.
yeah.
So this works as a fuse and it just doesn't.
Yeah, wire
It works as a fuse. It just doesn't pop. It gives you a light instead.
Must have popped pretty hard.
Just no grip.
So there is our blown 3-amp fuse, which he found pretty efficiently, turned on and then blew. So now we got to figure out why that's happening. What we don't want to do is just keep putting a bunch of these in there and wasting them. So we replaced it with a short pro to save fuses.
We're using something else.
If our transformer's not even.
Oh, okay. Where did that come from?
Sam, it's got a reset button on it,
Okay.
which is right here.
Yep. So that one will just trip. Okay, that's a good one. When I'm using these breakers, I always prefer to use the 3-amp rather than the 5 because they're going to be more prone to trip more quickly.
So we don't damage
Just
anything.
so we don't damage any circuits. Exactly.
Yep. Go ahead and turn off the power. Whenever you're opening up electrical box like this that maybe potentially has a loose connection inside or has high voltage, kill your power first. Same thing he's doing here. He kills the power before.
Is this just resettable?
Well, there's a fuse here, but we haven't needed to check it because that's our 24 volt thing is after, yeah.
Right.
So
We're using something else.
if our transformer's not even putting out, then we're not worried about the fuse yet. There is voltage back there, so
Yeah.
what's a better way he could do this?
Okay, take this door off.
You could pull the disconnect. Right, this would be, I guess this is symbolizing our breaker panel, so you don't have that option on the breaker panel.
Or we could unplug it.
Yeah. So we'll go ahead and take this off. We do have a plug here that we could unplug, but you wouldn't typically see that on the unit. This symbolizes our breaker panel in the garage. You're gonna have to take that off unless it's sketchy like that, then you can kill main to the house before you take it off. Nobody sees our problem yet? Anybody?
In here?
All right, Mario?
Yeah,
You're right. What circuit are we dealing, what voltage are we dealing with for a furnace?
I mean, yeah, 120.
120, you're right. And so we've turned on, we have both of our,
And then you didn't turn off the
We had them all on.
were they all on?
Yeah.
Oh, okay. Well, maybe Brian set up our problem inside our electrical. I thought you only turned on this one.
No.
Okay.
They were all on.
All right, so now we got them on. Let's find out if we're actually getting voltage out. Checking between hot and common coming out of the breaker. Between hot and neutral. No, so we have
incoming power first, right?
Yep. Go ahead and check the incoming power first. That's not actually our incoming, that's our condenser. So your incoming is going to come into the top of the bus bar.
Yeah. Right.
So you have 240 and then neutral. So let's check our 240. Well, we're going to check between our 240 first. So we have 240 and a neutral. But we're going to check 240. That will allow us to check. Oh, you can't see it. That's what your problem is. See
There it is.
Yeah. Okay. All right. So our main breaker is off. Be like the same as a main. Yeah. You want to go? So we're just slowly chasing our power back to its source, apparently.
So you need a new breaker. No.
A new main breaker for the house?
Yeah.
That would be commonly that you would check the main breaker, and if you weren't getting it there, it would be an issue with the meter or a power supply to the home.
Yeah.
To check one leg at a time, then you would go to ground.
Yep, then you would go to neutral would be the most accurate there.
Neutral.
Yeah. Instead of ground to the box, yeah. So apparently the entire training unit was not plugged in. I hope that's actually what we're supposed to be finding. Otherwise, we're going to plug it in and then start over and find the real problem that Bryan created.
Short Pro just uses a light as an indicator, so you're not actually tripping at all. All right, so now what are we going to do? So now we know we had it blew a
It blew a
fuse.
fuse and it kicked on and off.
Right.
Which means we weren't getting 24.
Well, we weren't getting 24 because the fuse blew. Right. So now, what type of system fault do we have?
We have a short.
We have a short. Okay. So now we need to identify where the short is exactly, and we want to figure out exactly which circuit it's in, and then we can figure out exactly which conductor it's in, and we can do that a couple different ways. But I want you to approach it however you would want to approach it first.
So normally, with this, I will unwire, separate my air handler wire going to my thermostat and my air handler wire going to my condenser.
Okay.
And I like to wire nut them and ohm them out.
Okay. So I'm fine with where you started there, but don't wire nut them and ohm them out, because wire nutting them and ohming them out is the test that we did for an open, not for a short. So we're looking for a short right now. So I would suggest do the same thing. Pull them out, unhook them, but do not unhook common. Do not unhook common. We need to keep the common intact in case that's where the short is shorted to, because that short that's blowing the fuse could be shorted to ground. It could be shorted to ground, but it could also be shorted to the other side of the circuit, which is common, which electrically on this unit is the same as ground, because the common is dedicated to ground. It's actually grounded on the common side.
So just another way to approach it, I would unplug the low voltage wires from the transformer and just start sticking meter leads into wire nuts to find the circuit that's shorted to either common or ground. Now on this one, the way that plug is, it would be once you unplug it off of there, you would still be bonded to ground on your common. So, I mean, I would just pull those two off and start there.
So you would actually just start by
Multiple blue ones.
I would pull these two wires off and just start sticking leads in wire nuts.
just ohming directly to. Okay. So I want you to use Eric's method before you use my method.
Well, let me get the correct size wire nuts on this.
Somebody
so
put
they're not
some
falling off.
falling off all the time. Okay,
Yeah,
I appreciate
yeah.
that. All right, look at that.
I didn't. They just kept falling.
All right, so Eric's method is using an ohm meter on a de-energized circuit, which is better for a couple reasons. One of the reasons that it's better is that you're not going to shock the circuit by continuing to energize it. And the other thing is that if we can get good connection without pulling the wire nuts off, this is the only downside of this. It's a little bit more of a pro move. If we can stick in there and get a connection to it on the other side of the wire nut, we don't even have to pull the wire nut off.
I would also be doing a good visual inspection, though, on any of the field wiring connections and even the factory ones to make sure something's not rubbed or crossed.
Or a brand new install.
Either way, it doesn't matter.
Good question.
If it's a service call, as soon as I take off the panel, I'm looking at the wires that are wire nutted all together, and I'm trying to confirm what wires they have going to where.
Right.
Potential damage
Right.
that I'm concerned of it.
Right.
No exposed copper, and also wire nuts, the correct size wire nuts, and
Yep.
that they're actually connected correctly together.
Yeah, and that's a good point. And also look if the thermostat's exactly if somebody recently replaced the thermostat. So does it look new? That's an indication, because that happens all the time. What's a common mistake that customers make that results in a blown fuse when they wire up a thermostat? They don't shut the power off. That's a common one. And the other is that they'll
The equipment with the reversing valve.
Yep.
And also making sure that it's set up, not that the thermostat doesn't come factory for straight cool or factory for a certain way.
Yep.
And changing it over.
That's a big one. Another one is a lot of, and this isn't the older ones, but a lot of thermostats had a B terminal, and they would say B blue. They would hook blue to the B terminal, but B is actually the heat mode reversing valve call. And so when it goes into heat, it would blow the fuse that way. So you'd get a bunch of those calls.
211. Yay, we have power.
Got power. Now we start all over again.
Our blower's running. This is pretty exciting. We currently are not blowing a fuse. We have a blower running, but our condenser has not come on yet. We're not going to be able to cool this customer's house without the condenser coming on. Are we in cool mode? All right, cool on is flashing, so our thermostat is in time delay. It'll only be 5 minutes. Delays can take a long time.
It's really easy to take off the
Go ahead.
delay.
All right, so Jessica looked up the manual on the thermostat. She's going to remove the time delay, and we won't have to keep repeating this time delay process. To save time, instead of, because we can't immediately find this model online, we're just going to bypass the thermostat, because what's happening is that the time delay just keeps repeating. So we got something causing a short in the thermostat, or an overcurrent, or the thermostat is experiencing too much load and it's just resetting the time delay. We're just going to bypass the thermostat just to try to figure out what the problem is. So how can we do that?
Wire nut.
Wire nut, okay, go ahead. And what are you going to wire nut?
R, G, Y.
Okay, she said R, G, and Y. So what is our G call going to bring on? And our Y call? And why are we connecting them to red? Constant power. So then we're going to take a wire nut and we're going to jumper red, green, and yellow. And hopefully figure out why is our time delay resetting. Every time it expires, goes across 5 minutes, it resets. So we're going to try to figure this out. You picked up on something, you could hear it. So immediately, we don't have our blower running, which it should be. We're getting the signal for the blower to run, and the condenser's not running. And it looks like we have an error code.
I think the fuse blew.
What's that?
The fuse.
Okay.
What's the error code?
So how can we make sure the fuse is actually blown?
Oh, panel's over there.
We could either ohm it out
Mm-hmm.
or look at the top.
So we could either ohm it out or look at it visually. If you look in through this fuse, you'll be able to see we have a black mark where it's actually burnt, and you can tell it's popped. But let's go ahead and test that with my meter. We're going to find out if we have a path. Still reading infinite, we don't have any path. So we've blown a fuse.
Moving on to Eric's method here. So we're going to use the ohm meter. So we have it on ohm scale right now, right? You're always going to, there you go, exactly. Always double check. And so now,
you're going to have to unplug both wires from the transformer, or else you get a false reading.
Right, back feed.
We already checked this, so we know power's off.
We know power's off, exactly, yep. So you're pulling the wires off of the secondary, so both your common and your hot.
And then your way, am I checking from common?
I would check every wire nut to ground first, because your common's still bonded to ground the way that spade terminal is on that transformer.
Yeah, if you see what he's saying here, the common, your ground and your common are still connected together. So you can just, well, you don't even have to, just touch it to ground. Just touch one lead to ground at that point.
We're getting potential there.
What are you getting as far
14.
as ohms? I wouldn't be worried about that.
Okay, so this is why this is a pro move, because you're noticing now you're measuring the ohms of the load, because you're going through the entire circuit now. Exactly. So what you're looking for is not 14 ohms, you're looking for something much closer to 0. So go through each one and find the one that's much closer to 0.
On a system like this, I'd be most concerned with stuff in single digits, because usually the compressor contactor is the biggest load and it's around 10 to 15.
Carrier is a sponsor of our podcast, and we're very thankful to them.
Really?
Yeah.
I actually really love Carrier.
Yeah, good.
There's 2-stage systems what I want to put in my home.
Okay, great. So this is the trick, and this is why I don't love this method for a newer tech, is that they've got to make sure that they've got really good connection inside each wire nut. I've already mentioned that.
You could take wire nuts off if need be, if you're not getting in there with your meter, and you don't have to pull wires apart though. You could, like he just did there.
So that is common. So yes, you're going to get 0 there, because that is common. All right, so what do we got there?
We have 1.2.
Okay.
Very, very low.
All right, so what does that tell us? What's the conclusion?
That there's a short because it's taking a shortcut off of the loads that it's designed to go through.
Okay, so it's a short in what conductor though?
In the blower.
What conductor is that?
Green.
Green, got it. So, or G. So now the next thing I would do is I would actually disconnect these from each other and check them individually to ground to figure out, is it maybe somewhere, going back to the blower, or is it actually that conductor? So in this method, we disconnected from the transformer, so we're not using voltage, we're doing it de-energized, we're using the ohm meter, and now we're measuring a low ohm path between G and ground, specifically because on this transformer, G and ground are bonded together. They're connected together. Not G, common and ground are connected together already. Now, that's not always going to be the case. So you have to think through all that. So there's a lot to think through. Good way, but now let's do it my way, which is going to prove the same thing.
What are we going to do next?
Put on the Pro Short tool so we don't blow another fuse, so we don't go through a bunch of fuses.
So what did we learn from our previous experiment about the fuse blowing? What did we learn from the unit running already?
Well, the blower was running earlier,
Without any problems?
so it's gonna be Y.
So,
It's gotta be on the
okay.
Y.
And our time delay is connected to our Y call.
So it tried to run and it reset because it wasn't getting.
So now we could disconnect the Y.
Yep.
And
And see if
connect,
it
leave
comes-
the other two connected and see if the blower
Come on with
Okay.
green and red.
All right, what are we going to need in order for this to work? Something
a reusable fuse.
The Pro tool, where is the Pro
so we're
tool?
going to use the reusable fuse that was out here so we don't burn through a lot of fuses. Okay, so we don't have a short there right now. What's the rating on this, does it say? Yeah, 2.2 amps. So this should pop at 2.2 amps. And the one that blew in there before was a 3 amp fuse.
Put the Y and see
Yeah,
if it.
so now we connected our red to green and it's running, it's not blowing anything. Yep, so now we'll connect red to yellow. Probably just be able to touch them together. There's enough room here that you can probably touch them together and see what happens. Yeah, it's immediately dropping out. Okay, go ahead and,
Our light came on, signaling there was a blown fuse.
yep. So our light came on, signaling us that we had too much voltage. So we got a short on yellow. So how are we gonna find out where this is? Where is our overcurrent on yellow?
You start at the condenser.
Yep, go ahead, open. A good short investigation starts with a visual inspection. And if you don't see anything obvious, start looking elsewhere. So this is a straight cool. We don't have a defrost board to worry about. Do we have low voltage switches? Low pressure switches? Looks like we don't. So our path goes straight to here.
We still have power.
And then we have our low voltage wire running down along here and back to our board. So it could be anywhere in there, right? Why don't we use the meter to try to isolate where this short might be?
And so can we do that by tying the wires together, like you said before, and then test it?
With continuity.
Nope, so we're not looking to see if we have continuity. We know we have a path already, we just have a path to the wrong spot, which is most likely ground. That's probably the first thing I would check. So if you were to disconnect your yellow and then take your meter and test between yellow and ground, you should have no path between yellow and ground. So we could ohm between ground and yellow and find out if we have a short on the ground somewhere by doing that.
All right, we'll turn it off. You want me to turn it off?
Yep. So let's go ahead and turn off voltage. We don't want power while we're trying to do this.
So now, plug those back in, disconnect all of your wires from each other other than your commons.
Everything but commons.
Yep.
We're leaving the condenser connected as normal.
Yep. We're just actually okay. Since we already know which circuit it is, we're just going to do this one just to save time. So you can leave everything connected, other than this one. Now we're going to energize. Put all your wire nuts back on, other than your G.
So next time you take this out, and then you get this little sticker thing that you can put a zip tie through. And you zip tie them right down here, all nice and neat.
Nice and neat. Yeah. I really don't. Yeah, I don't like that little.
This is just a potential.
That's how they get their UL rating.
Really?
Because it separates
because it's
thermostat wires
from the yeah. Okay, so now before we energize in this case, because and this is the same kind of test you do, what we call the redneck test on your compressor. It's like the last test you do to make sure that is the circuit, because before it was tripping the breaker, right? Mm-hmm. Now we're going to go ahead and energize it. Safety glasses on, energize it, and see if now with G disconnected, does everything else run as expected? Does everything else energize and run? Because I'm trying to take a shortcut here, in order for this to work properly, we still have to disconnect everything. But something interesting is happening here. This finally tripped, but you saw it tried to run a couple times. The thermostat has an overload protector in it, so when it sees too much current, it actually starts resetting, and that's actually an issue that we had
with a couple models of thermostats where it made it hard to diagnose short circuits because it would actually just sit there and stay in time delay forever. It would never come out of time delay. So that's something that you will see in some cases with short circuits where it won't trip the fuse because it never allows it to stay energized long enough. All right, so now let's do it the proper way. Shut off the breakers, let's disconnect everything, and I'm going to show you the way that I would typically confirm it in one pass for a newer technique.
If you have the thermostat doing that, especially on the newer ones where you pull the base off the wall, it disconnects the thermostat from all those wires, so you could sit there with jumpers.
Yeah, that would be another way.
Just making sure.
Yeah, just double checking. Yeah, yeah.
I don't want to get shocked in front of you.
Okay, so now listen, most of your systems, common is going to be tied into ground at the transformer. So if you leave common hooked up on the circuit like it is right now, then you're going to get a path to ground when you check yellow to ground, because it's actually going to travel through your load and back to where it's grounded. So you're going to want to disconnect common during this test so you can actually see what's going on there. Yep, so he's got yellow to ground.
I would have checked from inside.
Yeah, at the air handler. That would have been just fine. Yep, check ground. That wire, your wired, yeah, your actual wiring. That's good. Okay, so he's not getting any path. Now what yellow are you checking? You're checking the yellow going straight to here. We're supposed to be checking the wire, the low voltage wire. Okay, any path there? So according to the meter, we don't have a path on our yellow thermostat wire between here and connected all the way back to this unit. Okay, and remember what we said about common? Common is grounded at the transformer. So there should be a path, which is why we removed it, so we wouldn't get confused by that. So if we don't have a short, anybody want to start trying to fill in where could this be happening? What could be going on?
Transformer. I mean, contactor.
Could be contactor. What would the contactor be doing that would cause a short? Chattering. That might happen if there's a short or a voltage drop. So what is a short? What did we talk about a short?
Something happening that,
Undesign path.
An undesigned path.
something happening that shouldn't be happening.
But what causes a blown fuse?
Short to ground.
Overcurrent. So we got too much current. This one was rated for 3 amps. If it's not a connection to ground, like let's say it was rub out on ground, that would be a path for the current to take without any resistance, right?
The amperage.
But if you notice, we already checked common is hooked up to ground and the other side's hooked up to yellow. We do have a path back to ground through the component. Why doesn't it blow a fuse? What slows down the current? Resistance. The coil. Where's the coil? Within the contactor. Exactly. So that coil actually generates a load that creates resistance, and it slows down the current that's trying to get to ground, but it slows it down enough that we don't exceed 3 amps. We don't pop our fuse. So maybe we have an issue there. Maybe we have an issue with our...
We gotta check the ohms on the...
Yeah. So let's check the ohms on the contactor.
So to Eric's point, again, and this just comes down to the irritation of disconnecting wire nuts. You could just pull the thermostat off the wall and do it there. So now you're jumpering each circuit, because what we're trying to find now is which circuit, which conductor is shorted, which conductor is tripping the breaker, right? Now we already know because we tested it the other way, but I just want to demonstrate how this would typically work. So now we have to, not the common though. Common, whenever you're doing this test, leave common completely connected and disconnect everything else. No, in that case it doesn't matter, but you have to have that path connected back.
One thing to keep in mind too, you may not see a lot around here, but I used to see a lot, is in apartment buildings, they would join the condenser to the thermostat and the thermostat to the air handler, so your junction wouldn't necessarily be in the air handler. Keep an eye out for that and attack it accordingly, because you'd have to approach it different.
Yeah, it is making it into a real rigmarole, isn't it? All right, we good?
I left this one on, but I disconnected both flows.
So now we have our R circuit, our red right here, and we can just use this one. So we're going to take each conductor now, and we're going to touch them individually to that.
In what setting?
And we're not going to use a meter at all. So this is a meterless test at this point. Now what we're doing, so go ahead, power it on. So common's still connected. So it's still connected to ground, everything's connected, the circuit's still intact.
But now I have 24 volt power right here, right? Or at least I should. We can confirm it. Go ahead and confirm that.
From red?
Yep, we're just going to confirm we have 24 volts there. So now we're going to take each one of our circuits and connect to our 24 volt power supply. We've confirmed that we have it, and we're going to find which one blows the fuse. Yeah, just start wherever you want. Does it blow the fuse? No, it doesn't, so it's not that circuit. Go ahead and go to green now. It took a second, though.
It took one.
This is what I don't like about these breakers, because even though that's a 3 amp fuse, did you see how long that thing took? Like, these things are notorious for burning up transformers.
That's why the smaller the better.
Especially the 5 amp ones.
Yeah, the 5 amp ones I've had all kinds of. So that's why I prefer Short Pro, because it just doesn't, it has high resistance in it, and so that prevents it from causing a problem. It just basically, the light lights up.
This is where things can get tricky. Jessica, what's the load called through a contactor?
The load.
Yeah, the resistive load. It's a different type of load than like a light bulb. Inductive load. Okay.
I would say conductor.
0.6. Yeah.
I thought you said 26.
No,
All right, so 0.6. So how much resistance is that? Because ohms is reading resistance, right? How many ohms are you reading when you have a path like this with
Zero.
no
So
resistance?
It's very low.
So we got 0. We have almost no resistance across that contactor.
Usually they're like,
Probably not. Let's find out though.
Looks pretty crispy.
It actually was stuck closed, but I don't think the contactor actually.
was that mine?
Let's test this one. It's
That
another
was
old
mine.
Hands a little shaky there, Bert. 10
Yeah.
to 15.
What is it?
10 to 15.
Yeah.
It's 2 poles, so probably like more like 10.
Yeah. So this one's 14.
Back.
The load that this produces is actually generated once the voltage has been applied to the coil. It's a load that's generated by the magnetic field. So you have a magnet that pulls in and that generates resistance. But if we don't have electricity on it, then we can't measure its true resistance. At this point, we're just basically doing a test to see if we're anywhere close to where we might be. 0, we're not anywhere close. 0, that's no resistance. So we had 0.6, just pretty much no resistance across that. That's going to allow the electricity flow straight through and go to our common, our other side, without any resistance. It's going to be way too many amps. Pop that fuse. Or what were we experiencing instead of the pop fuse?
It was causing the
Time delay.
the time delay.
Yep, time delay to reset. If this was a heat pump unit, you often see it causing the time delay inside the defrost to reset. Boom, 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 because it's too much current and there's an overload either in the board or on the thermostat that drops it out.
Would it be safe to say that in a blown fuse scenario, you could kind of, I mean, and I know we shouldn't make any guesses, but
Yeah.
you can kind of surmise that most of the over amperage is going to come from either the outdoor unit, the condenser, somewhere within that circuit, or within the board at the air handler.
Usually not the boards. Boards are usually where people are going to guess for shorts and stuff, but like what you said first is a lot more likely. Something outside in the weather, something exposed to people knocking it, messing it up, something exposed to the sun.
Rodents. whatever.
Rub outs, yeah. Look for those points first, which is why we tested the ground first, because that's typically where you're going to see it. So what's a way that we could, since we've measured 0, we know that's wrong, but how might we figure out what a capacitor should, or a contactor coil should be?
Testing a good one?
Testing a good one. Do we have a good one? All right, so we got 14 across this, yep. So you can pull contactors out of your van. Jessica's bringing another one. What do we got on this one?
Out of the box.
Out of the box. And you can get an idea of maybe where you should be on a relay, a 24 volt coil by doing this. This one's 12. So typically you're going to see between 10 and 15. And then when you start getting lower than 5, you know that thing's pulling way too much current. There's too much resistance on there. So let's pop it in.
So now we're going to power it up. First thing we're going to do is look for symptoms. So like what's happening.
Hey, that's not right.
What's
Also
not?
want to check. It looks like it's running in heat right now because I got cold air coming out of here.
Okay,
I'm
so
also going to turn off. I'm going to turn off the outside because I can't really hear. I'm going to see if the blower's running.
okay.
Blower's running.
Okay. All right, so what's the conclusion?
Well, so far I know that the orange is not energized.
Okay.
Reversing valve should be getting energized to turn into cool.
Right.
That's not happening.
Right.
This turned on fully, so I'm not going to look at it.
Okay. So blower turned on.
Yes.
Compressor contactor pulled in.
Yes.
Reversing valve
Did not.
solenoid is not energized, so it's running in heat mode. Okay. All right. So what energizes the reversing valve solenoid? Thermostat, right. What terminal on the thermostat?
The O terminal.
O terminal on the thermostat, right? So, but what route does it take?
Just goes from thermostat to air handler to this connection.
Right.
It goes through and goes to the condenser.
Exactly, right. And so what are some things that could cause this? So let's think through that first.
Okay, one common one that I've seen would be these weren't properly stripped back, so it's getting an inconsistent connection.
Right. So a poor connection in between your O, right? Field connections, always a place to look.
Let's say it's old and maybe they ran it through the attic. Somebody could have nicked it in the attic and cut
Yep.
the orange.
Yep. Where does that circuit end up though? Like where does it actually connect when it ends at the very end? It goes into the condenser, but once it goes through the defrost board, where does it have to go? Where does that circuit actually end up? Like the Y circuit ends up on the compressor contactor coil. Mm-hmm. The O circuit ends up where?
Ends in the defrost board.
That's where that conductor ends, but that's not where the circuit ends. Because the O terminal doesn't energize the defrost board.
Yeah,
what does it energize?
It energizes the reversing valve.
But what on the reversing valve doesn't energize?
The solenoid.
The solenoid, which is an electromagnet, right? So there's an electromagnet that attaches to the reversing valve, and that's what it energizes. So it could be a lot of different things. It could be that solenoid is off. It may not be an electrical problem at all, right? So there's a wide range. Could be programmed wrong. There's a wide range of visual and just sensible things you'd want to go through first to make sure. You'd want to look and see, is the coil attached to the reversing valve? Like you mentioned, do I have poor connections in obvious areas? Do all those first, and then pull out your meter and confirm, do I actually have 24 volts? Or you can do it the other direction, whichever way you prefer. I always prefer, especially for newer techs, start with visual, start with everything you can check, and then don't be afraid to pull your meter out, but don't lead with your meter. Okay. All right, so go ahead and do that. Let's go through it and see if we can figure out exactly what's going on.
I think we've isolated our problem pretty clearly. Let's put another one in.
Power's off, right?
Power is.
And we should always test anyway.
You should always test anyway. Good call, Mario. How do you check for power in a safety scenario to make sure you're not going to get shocked?
You go to the incoming. Yeah, there's the
incoming power, so he's checking for 240.
And then I'll check for 110 off each blade.
So he doesn't have 240, and then what's the next step? To ground. Because when you get shocked, you are ground. So if you don't have a path to ground, then you're safe as ground. I wonder where this one came from. It was just sitting right over there. So once we started looking for this, we used the light and we used the fuse to kind of bring this down to one wire. And then we broke out the meter. But we could have started with the meter. You could have tested green to ground. Okay, I have no path to green to ground. You could test yellow to ground, no path there. That would eliminate those wires having a path to ground. That's not why we blew our fuse. Then you could move on as we did. So understanding how to use your meter appropriately a little bit more saves you on replacing a bunch of fuses and relying on other tools that something like this, which isn't super reliable. The light might come on, but sometimes it'll actually allow too much voltage through still, and you'll blow up your transformer just from experience using some of these tools. I don't know about that model in particular, but the ones I've passed out before, we ended up just burning up a few transformers in the process of trying to figure out a short. Can you pull the old one out?
Yeah.
Okay. Now, it's a little easier to put the new one in and then attach them.
Yeah.
And if you do wire for wire, you can leave the old one hanging.
Okay.
Instead of the new one hanging. It's just going to make it easier, that's it.
All right, Eli, come on over here. He needs some help. We've got it. He's in his visual inspection phase here. His system's running in heat mode. So we talked through some things that you would definitely want to check, but where do we want to look? So definitely, if you haven't looked at the reversing valve yet, just take a look at it and make sure, is that coil attached to the reversing valve? It's running in heat mode. All right, so you've identified the reversing valve, you've identified it's attached. I would probably go through, if we hadn't already just done it, and check the thermostat settings next to make sure that the installer setup is set up properly.
We know we checked it earlier, it's at the 5.
We just did that, so we're not going to go through that again, but that would be the next thing I would probably check. What are some other things? What would you do next, Eli?
First, I would check at the condenser to see if it's receiving 24 volts on the bow wire.
Okay.
If it's not receiving it there, I'll follow it up to the air handler, see if the thermostat is sending 24 volts to the air handler.
Right, now I don't know if we addressed this yet, but what kind of problem do we have here? What category of problem is it?
We have an open.
We have an open. Correct. It's not a short, so that's what we're looking for is an open, which is good because we don't have to mess with fuses or any of that kind of stuff. All right, so let's grab your meter and let's fire it back on and check to see if we have 24 volts. I would just check it out. Check it outside, like Eli said. You're not turning on the condenser because we don't need the condenser to short cycle right now. We just need to see, are we getting an O-call from the thermostat through the air handler? All right, so we're checking from orange to common, and we have
A little bit of ghost volts, but nothing.
nothing really, right? So that's an indication of what?
This is not getting it off.
All right, so now at this point we don't have to focus from here in because there's a lot of stuff we could check from here in. You know, we could check.
If this was energized, then I would check the solenoid.
Exactly, you check the solenoid, you check the wires that lead to it, but at this point we don't have it there. So now we still suspect, all right, could it be that the thermostat isn't sending an O signal at all, right? We don't know, it could be. Or is it that it's broken in the conductor between the air handler and the condenser? So now I would back in and check it at the air handler. And you could have started at the air handler. I tend to start at the air handler, but either way is fine.
When you're out of the condenser, it's typically...
This is where you would, because right, so to Eli's point, you're at the condenser, that's where you found out that it's running in heat. So you might as well check it there, exactly, yep. You know, start wherever you are rather than running back and forth. Now again, whenever you're going to test within a wire nut, you have to, you know, it's hard to trust. You know, so you would want to check to like another circuit too if you do get a case where you're not measuring anything.
Okay, so I am getting 24.
You're getting 27 volts at
the connection in the air.
Correct, between your thermostat and your air handler.
My air handler. So at that point it would be between the air handler and the condenser?
Between the air handler and condenser, what?
Between the thermostat wire coming out of the air handler to the condenser.
There is a what in that wire?
There's an open.
An open in that wire, exactly. That's what I was looking for.
Okay.
So that is what you want. Now let's go ahead and confirm that with an ohm test. Normally this is where you'd stop. You don't need to do any more at this point, but let's go ahead and do it with an ohm test. Now, actually, quick caveat: you would at this point want to dig back because again we have these underground, you know, thermostat wires. You'd want to dig back and see if you could find where the break is, anywhere that you can visually see, because that's going to be most common, right? Somebody weed whacks it, whatever. Don't immediately jump to, you need a new wire, right?
Old bad splice they did.
Old bad splice, exactly. Or sometimes people will splice some conductors and they won't splice them all. You know, that's another common mistake.
We did an install and we reused the line set and low voltage. That's what they wanted to do. And we had like different colors outside than inside, and
Right.
only some of the conductors were spliced.
Right. Whenever you're splicing...
It was a straight cool before with a furnace, so we
Right.
went to a heat pump, so we needed more conductors. Luckily, we found some that worked, but that was...
Yeah, anytime you are splicing wires, you splice all the conductors. If you got 8 conductors, you splice all of them. That's the first thing that Dave Barefoot taught me. Actually, I don't know if it was the first thing, but it's something he taught me. All right, so now we're going to go ahead and use an ohm meter. So power it down. You always only connect an ohm meter to a de-energized circuit. So de-energized, and now we're going to either way. So we can do it on either side, but you're going to take your orange and you're going to connect it to a different color on that same cable. So and ideally you would connect it to one that you know is working.
Oh,
so
I knew this one was working.
But again, right now you're connecting to the one going to the thermostat. So just make sure you're using the conductor that's actually going to the condenser. So we're just going to connect these two together. Okay. And then outside, because see these are in the same conductor going to the outside.
Okay.
So we're going to connect these together, and then we're going to go outside, and we're going to check in between orange and yellow and see if you have a path.
To wire them out on this, or can I just take it?
You can probably, in this case, because we already know it's an open, we can just go ahead and do it that way. Normally you'd isolate them to be sure. So as long as you know those are pushed in there really good and they're making good contact. So in this case, what were you just measuring between? Orange and yellow?
That's So
Yeah.
there's a wire not together in there.
So the problem, you see we have 29 ohms, so we are getting a backfeed. You would want to go ahead and actually disconnect them. And that's the problem. When you're connecting through boards or anything like that, you can get a backfeed. So because these two are connected on this side, we would expect to see 0 ohms between them. And instead we have infinite ohms, which is another proof that our orange is open. It's broken, correct. And because we knew that the Y circuit was intact because the condenser was running. So we don't have to do any further tests on the Y circuit. We know it's intact, and that's using what you remembered about the initial test you did and the status of the equipment. That is really critical in diagnosis. You don't want to rush ahead and start ripping stuff apart, because then you get halfway and you're like, where am I? You know, like now I don't know what's what. It's always good to make every observation you can make before you start disconnecting everything. But in this case, the diagnosis, Tanner made it correctly. Open orange conductor in between the air handler and the condenser. And so at that point, your only option would be to either rerun a whole new wire or utilize a different conductor. And in some cases, that's your only real choice. But generally speaking, if you've got one conductor compromised, it's only a matter of time. But often you can actually find it. You can, figure out where it's compromised and fix it. Wire nut it in the dirt. Yep. The summary of this class is what we've essentially done is in this case put a failed contactor, one that we knew we had a shorted coil in, and it took a little bit to diagnose in this case because of why.
Because main power coming into the unit was off.
Okay.
Yeah, and that was a whole nother step.
Okay. Yeah.
Secondly, the thermostat's time delay kept resetting, so
Right.
we never actually saw the unit try to come on, and it would reset before it actually blew the fuse.
Right,
We never
which
saw
is
it.
actually a real problem, and it depends on the thermostat manufacturer. That can happen. So that thermostat, when it has that inrush of current, rather than even allowing the fuse to trip or energizing anything, it just stays stuck in time delay. And certain thermostats do that. I actually mentioned it, and then we had one that had that circumstance. Go ahead, you were turning your mic on like you were going to say something.
I was just going to reiterate, I don't know if we went over it, but a short could be a failed load, like they had in that
Correct.
unit, where the internal load in
The load
device
itself is shorted, yeah.
shorted, not
Yeah,
an
it's
external
not an
short.
unintended path. It was just.
I mean, it is. It's a path that is now lower resistance than it should be.
Right.
Yeah. And in this case, we went through an open and a short. So we had a short that Aaron found, and well, actually, my initial one didn't work because for some weird reason that I don't know. And then Tanner found the open circuit in the orange wire. So this is something that, in order to get good at this, you just do it a lot. And just like Eric and I talked about, there's many different ways that you can approach this. You can use the system voltage for diagnosis. You can use an ohm meter for diagnosis. And that's going to vary depending on your level of skill, depending on your comfort with that particular practice. But you want to be able to come to low voltage electrical diagnosis, most of them, within about 15 minutes. That would be a pretty typical standard thing. Now, obviously, if you've got a compound problem, that can be challenging, or a whole bunch of us standing around with cameras, that makes it a little more difficult. But out in the field, typical electrical diagnosis generally is going to be about 15 minutes. Wouldn't you agree?
Yeah.
Yeah, for residential. Cool. All right, thank you all. Great class. Appreciate you. Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.